let's get started.
Are you fine?
So, thing is, with this workshop, we usually just spend some time wrapping up everything we've done in the past workshops, and we spend some time for questions and anything you might have to think about what you want to do in the future with ML and AI in general. But the most common thing that people do after beginner track is taking ACM AI as a advanced track, right? And we have a few wonderful lecturers who will be taking that every quarter. So the ideal thing is you graduate from beginner track, you go to advanced track, and then you move on to product. So what we're trying to do with this workshop is give an intro to neural networks. And this is by no means going to be a comprehensive introduction, okay? I'm just going to motivate the idea of what a neural network is, because that's the first thing we touch upon in advanced track. So essentially you gain a head start. If you do some background reading, you'll probably enjoy neural networks a lot. And this is why machine learning gets interesting. This is why most of the research happens. So yeah, let's dive right into it. So actually go back to the previous slide. What do we have any announcements today?
No, it's week 9.
Okay. Well, no announcements for now, but we're just going to be talking about neural networks, what they are. I'm purposefully going to let some of your questions be. I'm going to leave this open-ended so you can think about this, and then, well, of course, we can talk about it later, right? We're going to talk about ethics and explainable AI, XAI, which is something that's up and coming, and we're going to see an ethics aspect of why people want to do this, why people are morally against it, and then we'll have some closing remarks where we can talk about what kind of sources we use to read about machine learning news, what we recommend you do after beginner track, which is, well, spoiler alert, advanced track, but we're going to try and give you as much context as we can. But let's jump right in if nobody has any questions. We good? Okay. So neural networks, and before we delve into neural networks, I want to talk about something called the MNIST Dataset, right? The MNIST Dataset is, I would say, by far the most popular dataset that is used for convolutional neural network training. Big words. We're going to talk about that. But essentially, this is something that we've used to train pretty much every model we have, which is done image classifying. And what this is essentially a data set with 60,000 data points, which look like this. Okay? And what is this? This is a 28 by 28 image, right? 28 by 28 pixels. And it's basically a lot of handwritten numbers. Okay, so it's numbers from 0 to 9. And what we're trying to do is we train our model based on this data set. And then once our model is ready, we feed in some random image of, well, a number, and our model should accurately be able to group that as the right number, right? And honestly, I think we've pretty much mastered our accuracy with this. I think there's an error percentage of 0.42, which is almost nothing in the grand scheme of things. So this is one of the most widely used data sets and something that you should know about generally. Next slide. Okay, so when we're in neural networks, okay, so I want to do a few things here before we get started, but more generally, the idea is I want you to think about how we interpret what number is this. It's 3, right? What number is this? That's also 3, right? And well, if I just do this, that's also 3, right? So even though all of these 3 things look very different, and when we look at them, there are different neurons in our brain that fire up, we can still classify these as the same thing, okay? Because some part in your prefrontal cortex is going to look at this and be like, this is a 3, this is also a 3, and this is also a 3, although they look very different. And at the same time, it will be able to say that this is not the same as this. This is a 6. And 6 may have a lot of different ways of writing this. If I ask all of you to come down here and write 6, it's probably going to look very different for all of us, right? It definitely won't be the same. And well, that's sort of something that we think about as we move forward, because essentially what a neural network is, by the name, is a network of neurons, right? What we try to do with machine learning is we take, well, a model and we try to train it, right? Like humans learn, we do machine learning, and we end up with, well, something called a neural network. Okay, and we're going to talk about this, but let's distill that into 2 things, okay? We have neural. Is this visible back there? well, I've written neural network if it is. Probably go back to the previous slide, right? And can someone explain to me what they understand by both of these words? I want to break this down and move very slowly, understanding everything that's going on. Can someone tell me what neural means? What a neuron is? Anything? Yeah.
It's like a brain cell, basically.
Yeah, pretty much. It's a brain cell. It's one cell in a huge network of brain. So brain cells. So what we're thinking about is this is a neuron, and I'm gonna just assume what a neuron is for now. But we have a neuron. We're talking about what this neuron is and how they're interlinked, and how we're going to replicate that in our machine learning model. How we're going to come up with a neural network which is very similar to our brain. Next slide. So for the purposes of this specific lecture, and this isn't exactly what it is, but I want you to think of a neuron as something, just a something, okay, that holds a number between 0 and 1. That's it, okay? So, well, essentially, I have this. This is maybe a 0.7. I have this. This is 0.9. Both of these things are neurons. That's how we're going to think of it. Okay? What is it? It's a something that holds a number between 0 and 1. Now, let's contextualize this within, well, the MNIST dataset. Okay? In this case, it holds the grayscale value of the corresponding pixel. What does that mean? If something is completely black, right? If a pixel is completely black, we're going to give it the number 0. And this number is called the activation, right? So every neuron has a number associated with it, and that number is called the activation, right? What the activation is depends on how we're classifying this. So we have 28 into 28, out of which some of these are going to be classified as 0. Some of these are going to be 0.5, 0.7, 0.3, and then we're going to have the ones that are entirely white, which will be 1, right? So essentially what we're thinking about here is it's 1 if it's lit up, and the activation is basically telling us how much a specific neuron is lit up. Do we have any questions at this point? Okay. So let's do this, okay? Next slide. So here's what I've done, okay? We have 28 pixels, 28 by 28, and 28 into 28 is 784. So for each one of these data points, we have 784 associated pixels or neurons, right? There's 784 neurons for now that all have an activation from 0 to 1, right? And here's what I want you to think about, right? We have this, and this comprises our first layer. So we're taking in a 28 into 28 image. We're representing it in the form of an array. And what we're going to do is work on this through a few layers. And then at the end, we're going to determine what the number is. There should be a 9 over here. I don't know what happened to that image. But it's going to be grouped as one of these 10 things. It's going to be classified as a number between 0 to 9. Right? And what we're going to do in advanced track mainly is try to figure out what's going on in these central layers. Right? Now, I've put about 16 neurons in both of these central layers. That's honestly an arbitrary assumption. That's not how it always is. That just fit better, right? So that's what we've taken for now. But what happens is we have 784 pixels. All of these have an activation. And their activation determines the activation of the next layer. And their activation determines the activation of the next layer. And that keeps on going for as many hidden layers as we have. So we have a first layer which we're aware of, a final layer which we have some idea of because we know we're going to get one of 10 numbers. And at the end, say, I plug in this, right? I plug in this. My model thinks it's, well, a 6. So what it does is at the end, this is going to have an activation. This is going to have the highest activation among them, right? So the highest activation in the final layer is the model's prediction. What goes on in between is something we're going to be talking about mainly in advanced track. But essentially, what we want to think about is what exactly could these layers be? Okay, and I want to talk about that for a second. And this specific layer here is one of the layers that is most commonly talked about. So what I'm going to do is I'm going to write a number, okay? And we're going to look at some features that numbers have in common, okay? Some features. So we have, for 9, we have this. We have 8. That's not the prettiest 9 I've ever made, but bear with me. So there's something common between this 9 and this 8. When we're writing it, we have a loop up top, right? We have this loop over here, and we have this loop over here. And for this, we have this vertical line over here, and for this, we have another loop down here, okay? So essentially, both of these things have something in common. So if our neural network can find that there is a loop, it knows that it can either be, well, a 9, an 8, or maybe even a 6, right? Because this is a loop down here. But if we can identify the fact that we have a loop somewhere in the image, there is a possibility that we can classify it as one of these. So ideally, what this penultimate layer looks like, this entire layer, this looks like, well, this isn't exactly how it is, but it will have one of the neurons is going to be a loop, one of the neurons is going to be a straight line, one of the neurons is going to be a line like this, one is going to be like this, one is going to be like this, right? So if the activation of, say, these 3 things light up, right, based on the previous layers, which we're not talking about right now, I have these various shapes as my penultimate layer of neurons, okay? And in this layer of neurons, if I have this one light up, this has a high activation, this has a high activation, and this has a high activation. My model is going to look for the number that has all 3 of these elements, right? It's going to look for that, and it'll say, oh, this looks like a 4, because a 4 has all 3 of these elements. So that's some idea of what neural networks are. And but are there any questions?
What are each of those? Oh, each of the circles are a pixel.
So each of those are the pixels. So we start off with 784 pixels, which will be called neurons. Okay. So we have 784 neurons, and in the layers after that, the subsequent layers, we have a different number of neurons.
Okay.
Okay. That depends on what the ML architecture is, and that's something we'll be talking about in advanced track. But we sort of determine how many neurons the next few layers should have, and how their activation is going to be governed. A number. Okay, we're thinking about a number right now, but they're also associated with strings, right? So they have a few things going on, but the main thing right now is this layer is going to have a few things. It's going to activate the next layer, which is going to activate the next layer, which is going to activate the next layer. And at the end, in the final layer, the number with the highest activation is going to be my model's prediction. Okay. So this is just a general idea of thinking about things, and obviously gets way more complicated and has way more math. If ML was this easy, everyone would be an ML engineer. But yeah, so that's it for neural networks, and we're going to talk about weights and biases, and I'm going to let Jackson.
Yes. So each one of these neurons is representing, well, we're not always sure what exactly it's representing. But when we have those neurons back in this slide, right? They are representing different like patterns that our model is picking up on, right? Like if you remember when we talked about logistic regression, we gave the example of like classifying, like a cat from like a dog, from like a fish, right? And stuff like that. And the way we talked about it was using features that were like, I don't know, like, if it had ears or if it had fur or if it had a tail or if it had fins, right? Now, usually our data is not that clear and concise, right? If we're building a program that's going to, I don't know, take in an image and do the classification we want, it's just going to be given all of these pixels and all like the RGB values. It's not going to be told, okay, this has fur or this has fins or this has a tail, right? And so it's up to the neural network to figure that out, right? And so for each one of these neurons, you can sort of think about it like it's taking from whatever input you have, it's pulling out some sort of like extra pattern, right? And usually it's not like as direct as like going directly from pixels to being able to tell you if there's like fur on whatever animals in the image, right? Because that would also be like really hard to do. Instead, what usually ends up happening is you start off with all your pixels and then, it picks up on some other pattern inside of it, right? Maybe it's like, okay, if I look at these specific pixels, and I do all of my math, I can figure out like how much it looks like there's a vertical line or how much it looks like there's a diagonal line, stuff like that, right? And so the way it does that is it takes in all of these input neurons, right? So like in this example, it's just the grayscale value of each one of the pixels and figures out how important each one is to you. So like, if say this neuron that we're talking about is telling us if there's a circle in the middle, right? If there's a circle in the middle, the pixels that are like on the very edge probably aren't super relevant to us being able to figure out what's going on inside the middle, right? And so because of that, we probably don't care that much about the value. When you compare that to, the pixels that are in the very center of the image, those pixels are probably a lot more important for us to be able to figure out what, if there is like, a circle or something going on in the middle, right? And so we take in these weights, right? And it's basically telling us how much is this individual neuron going to contribute. And then we can do the logistic regression equation, right? To sort of figure out if we're going to like activate the neuron. And then once we activate the neuron, we can then pass it on to like the next layer, right? And this is like the purpose of multiple layers is because, maybe the first layer just tells us if we have like, a cross pattern and like if there's a circle, stuff like that, which isn't like enough to tell us that, if it's like a dog or a cat. But from that, we can figure out, okay, if it's like this, if it's like this much of a circle, like this percent of a circle, and like this percentage like close to like a cross or whatever other features have been picked out, we can then like combine those and figure out like how similar it is to, I don't know, like, a skull or something like that. And then like with each layer, we're able to take these like basic features and make them a little bit more advanced. Yes, Ming-Yang.
So does it mean that all layers have the model is more accurate, or is it just like optimal?
Yes, well, so this is sort of a case of like diminishing returns, right? Because there's a ton of linear algebra and math that's going on behind the scenes, if you guys remember from when we talked about logistic regression. And so adding more neurons and stuff like this means that it's going to be harder for us to run our model because we're going to have to do more math when we're training it, right? Because figuring out what the weights should be if we're just going directly from the input neurons to like the output is going to be a lot less math than if we have like 20 layers with 100 neurons in each layer, because each one of those neurons in the connections between the layers, we're going to have to figure out what the weights should be for that and do all the math for it behind the scenes, right? And there's also like a certain point after which the trade-off probably isn't worth it. If we are able to get a model with 4 layers and like 20 neurons to a layer that's able to do like 99% accuracy, in the only way to like significantly improve it would be to add like 10 more layers, and it would be like a 0.3% improvement in accuracy. At that point, you're not really doing much, and so it doesn't really work. And oopsie. Okay, there we go. And so you can also like see somewhat like weird behavior as like you can see behavior where like the loss like goes up and then like can go back down like a little bit again. Like usually you're not going to see adding more neurons is going to like completely wreck it, but like you can see it where like it results in like a small, but there is like a small like drop in it. And so there is like usually like a sweet spot. Now there's no super hard and fast rule. It really depends on your data and like what your goals are, right? So yeah. And any other questions, comments, concerns? All right. So this is an example of a single layer neural network, right? We have our input layer, which would be like the pixels. We have one hidden layer, which is basically we're taking in all of these pixels. We're figuring out like these weights that tell us how much they should affect these individual neurons, and then these neurons are like corresponding to like some sort of feature that our neural network has managed to extract from the chaos of all these different pixels, right? And then based off of that, like this could be, I don't know, like this could be a circle, this could be square, this could be like triangle, and then based off of like how much of a circle it is, how much of a square it is, and how much of a triangle it is, we can like figure out whatever we're trying to classify, right? Maybe we're trying to classify, I don't know, a diamond or something, or pentagon, I don't know, right? And so, this is sort of what I touched on earlier. It allows us to model more complex data because as we go through the different layers, we're able to peek in and be like, okay, we're going to pull out a small feature that we can do. And then from these features, we're going to build off of it and pull out slightly more complex features and go layer by layer until hopefully we're at a point where we can, get pretty good accuracy, right? And this is because in real life, things like image classification are not super easy or like intuitive to be done with a couple of steps. Like it's really complicated and there's like a lot going on behind the scenes. The demo here is pretty good because you can see our input, our inputs are like how much, how similar the data is to like these features, right? So it's like, okay, this one is like how much of a half and half distribution it is, and this one is like how much of or half and half, but instead of being vertical, it's horizontal, right? And then from that, we can figure out, okay, based off of how much of like a vertical distribution and how much of a horizontal distribution we have, we can figure out how close it is to like a diagonal distribution, or like, this one's a different diagonal. And then this one's pretty much corresponding, like just like the same thing. And so you can see that if we run it after like 100 epochs, it's pretty good at being able to like extricate the fact that we're looking for a circular pattern. So if we look at it, it's identified that the patterns that are most important are, if there's a diagonal line going like this, another diagonal like this, another diagonal like this, which sort of makes sense if you think about it, because if you combine like all of those diagonals, we can sort of see that they would combine to form like a sort of like circle in the middle. Does that make sense to everyone? And so based off of these, we're then going to feed it into two more neurons, which are going to figure out, okay, how similar it is to this pattern and how similar it is to this pattern. And then based off of those two patterns, it can combine it and figure out like this circular pattern, right? And so when we're doing like a more advanced one, like this one with like the spirals, this probably isn't going to be sufficient for us to create a super accurate model, because we're only taking in a couple of features and we have a relatively limited amount of neurons. So if we train, we can see it sort of ends up going like this, which is not really close to the behavior that we're looking for. But if we, give it a bunch more features, we can see, okay, like it's still not doing great, but it's a little bit more complex behavior. And if we add, let's add another layer, like I'm just going to throw a bunch of layers in, and if we add a bunch of these different layers, we should hopefully see that it's getting a little bit closer, right? And so this is not by any means perfect, but it's a lot better than what we had before, where it was just sort of like cutting it in half and wasn't really able to figure it out. This is also a really good demonstrator of the importance of good data, because you can see right here, there's this like little gap, and the reason why this gap exists is because we didn't have any orange data points, right? And we as humans looking at it can be like, okay, clearly this is not right. We would want it to be orange along here. But because there is no data to tell our neural network, like, hey, like you can't have blue here, it was like, okay, I'm just gonna make it work and I'm gonna put blue here, even though, blue might not necessarily be what we want, right? So this is a very fun demonstration. It's on the TensorFlow website, just the TensorFlow playground. You can, there's other distributions like, squares and like, 2 different clusters and the original one that we were on. And, you can see the effects of more neurons on, on the performance of your neural networks. And so if we go back to like the original one, we can see that we're able to get, good results again, but this is like a pretty decent example of a time where we didn't really need the more of the neurons, right? Because if you remember the last time we did this, there were only 2 layers and 4 neurons in one layer and 2 neurons in the next, and it was still able to get just about as good of a distribution, right? And so this would really just be a bunch of like extra math and like extra computing that isn't super necessary for what we're doing. So any questions about that?
I actually really recommend this specific thing, this specific tool. I use it a lot, and especially during advanced track. You're going to be exploring a lot more, things around learning rates, activation, regularization, and the regularization rates. So as you learn more about those functions and even optimizers, you'll be able to test and see how it actually works. And I think this is a much cooler demonstration of actually just going through.
Yeah.
Like the first time I saw this, I was blown.
Yeah, totally.
Yeah, and I decided to join ACM, so you should too.
Oh, also, the how like opaque the connection is between the neurons tells you how much like it contributes. So if we go to like this one, right? This is like a really like dark blue, and the weight is like 0.7, which is like a lot when you compare it to something like this, which is like a weight of 0.23. And that's because if we look, this, this pattern is pretty damn close to this pattern. So there's going to be a high level of correlation between the neural network pulling out this pattern, and if this pattern exists, we're pretty sure that this pattern is also going to exist because they're basically like the same thing, and we can see again, this one's another strong weight, 0.57, going into what's again basically like the same thing. But you can also pull out other weights, like this is 0.63, this one into this one. So yeah. All right. Now on to ethics, explainability of AI. So this one is very important. So as we've been talking about neural networks, right? You may have noticed that it's like a ton of math, but we really are not sure what exactly the neural network is going to do, or like what it's like pulling out, right? Because at its core, what the neural network is just a bunch of different weights connecting a bunch of different neurons, right? And so, on a smaller scale, and for certain types of data, like with the demo, we could do a pretty good job of figuring out what was going on behind the scenes, right? But when you think about something like ChatGPT, for example, I'm sure we've all used it, or at least seen it. That's something where there's going to be millions upon millions of weights with like a ton of different neurons. Like there's so much going on behind the scenes that it's really not feasible for us to be able to say, okay, well, when it takes in this, it's going to detect, like this, if it's this sentence structure, like it's just something that's like, out of hand. It's, we can't look at all of these weights and, figure out exactly what's the AI is like thinking, right? And so this raises a lot of like ethical questions, because, and this example is actually a very good one. If you're like a patient in a hospital, right, and the doctor comes back with a diagnosis from an AI model, how much do you trust this diagnosis? Okay, we fed your scans through, we I don't know, you're getting checked for like, tongue cancer, and like, okay, we took like some scans of your tongue and we fed it into the AI, and it told us, that it thinks that there's, a 91% chance that you have tongue cancer. A pretty logical question to be asking would be like, why does it think I have tongue cancer? And with like a human doctor, the human doctor is, well, if they're a good doctor, they should be able to tell you, right, why they think, okay, looking at your scans, we can see like this seems, a little bit cancerous, and these are usually associated with like early cancer warning signs or something like that. But if it was just an AI, we can't really ask the AI why it made this decision, right? The AI is just, it took in all this, it did a bunch of math behind the scenes, and now it's telling us this is the probability that it thinks there is that you have like tongue cancer or something, right? And even if like historically, say, a lot of times we can get AI models that are better than humans. Say, this is like a 98% accuracy rate on the AI model, but like a 95% accuracy rate on the doctor. Do you trust this diagnosis? Because the doctor can tell you why he thinks that, your scan was like a little suspicious or whatever, right? The AI model can't, and, the doctor probably can't tell you either. And like also, this is an area that's sort of like ripe for statistical like misinterpretation. Imagine a scenario where I'm like a skeevy businessman, and I'm gonna say, okay, I'm gonna make an AI that like detects cancer, but all it does is just, it says, no, you don't have cancer. Well, if you misrepresented the statistics a little, say, most people don't have cancer, so your success rate is probably going to be decent, right? If you just tell everyone, no, you don't have cancer, most people don't have cancer. So you could say, oh, we don't think you have anything. This is like a pretty solid, like, like this is 98% accuracy. And it's like, well, that doesn't really tell the full story. And like, if it's this black box, you are not going to be able to tell if like, it's doing any legitimate analysis, or it's like, stumbled onto something by luck and stuff, stuff like that. And so this is like a very big problem and something that's really hard to deal with. like, certain algorithms can be easily explained, but neural networks are very, very hard. Like if I gave you guys, a list of weights and, like told you, okay, it's going to do a bunch of linear algebra, tell me what it's actually thinking behind the scenes, you're probably not going to be able to do it. And so this is a very growing field, as it says here, XAI, explainable artificial intelligence. And personally, I think it's a fascinating one. So any questions about that? Comments, concerns? All righty, I'm going to hand it over to Claire then. Give it up for Claire. Woo!
Yeah, so just some closing remarks. So this is the last workshop of this quarter, and we've done a lot. So you guys have learned about algorithms like linear regression, logistic regression. We've also taught you Python, like NumPy and data analysis. And if you attended projects, you made linear and logistic regression from scratch. So those are all pretty cool feats. So thanks for sticking with us. So now you might be wondering, okay, this stuff was pretty cool. What do you want to do next? So a lot of the stuff that we covered this workshop is shallow learning. We've discussed neural networks, and so you can kind of see how they build off the topics that we've covered this workshop, but like extending it a lot, especially when you add like more layers and all of that. And we've done a lot using scikit-learn, which is what we use for linear and logistic regression too. But if you want to do more, then we can try other techniques in shallow learning, which is pretty much like the same area that we've been covering. These terms will probably be unfamiliar to you, but if you're interested, you can just go look them up. They're kind of similar to what we've been doing, but just different applications. And Naman has covered that we have an advanced track within ACM AI that will go more into things like convolutional neural networks and like backpropagation and things like that. So if you want to really learn more about like the details of machine learning, then we hope to see you in advanced track soon. And then we also have projects, which does things like computer vision, I believe. And then the newest one is natural language processing with Cora. So if you're interested in like doing something that's hands-on and then you have something to show at the end of the quarter, then we also have projects. Other than that, Medium is your friend. It was consulted many times while making these slides, and they have a lot of interesting articles on like new machine learning topics that you can check out. Or you can just like go look up things for AI news because there's always something new coming out. So yeah, that's all for this quarter. Thank you guys so much for coming. And that's it.
Yes.